Yes, sir.
Yeah, okay. Thank you. So we have discussed this ferromagnetic material. So already yesterday we have discussed ferromagnetic material. Mainly all spins are aligned in same direction. Okay, all spins are aligned in same direction, and because of this alignment we are having strong magnetic dipole moment. Okay, dipole moment. Okay, because of this dipole moment we are having strong magnetic field. This material, ferromagnetic material, show very strong magnetic field. Okay, so this is already we have discussed earlier. Okay, ferrous, this is iron. Okay, iron, this is the 26 atomic number. Here if you write configuration argon 4s 4s2 4s2 3d6. That means in d orbital only we can fill the in d orbital 5 electrons, right? We can fill 5 electrons. Here you can fill one electron. Okay, here you can fill one electron, but 5 you fill and one more you can add here. Okay, so here 4 shells are partially filled. That means these are showing high magnetic field because net spin is very high here. Net dipole moment or net spin moment is very high. Because of this one we are having strong magnetic field. If you keep this ferromagnetic material in external magnetic field, these lines of force, magnetic lines of force, attracted towards the center of ferromagnetic material. This will, suppose if you take the ferromagnetic material, it will strongly attract or strongly repulse. Okay, when it will attract, strongly repulse, suppose this is south pole, then it will strongly attract the north pole. Okay, if it is south pole, when you bring it south pole, it will strongly repulse. Okay, equal poles will repulse. Sir, second please. Here, if it is equal poles, it will strongly repulse. If it opposite poles, it will strongly attract. Okay, that is the meaning of strongly attractive and strongly repulsive. And here susceptibility is positive and large value, and it depends on temperature. We will see this one. Okay, chi is depends on C by T minus Tc. Okay, C minus T by Tc. Here always T is temperature greater than the this Curie temperature. Tc means Curie temperature. If you plot the graph, like this, you will. Okay, I will draw here. Susceptibility versus here temperature. It will increase up to particular temperature. After that, the magnetic field will decrease. This particular transition temperature we are calling Curie temperature. Okay, this law we are calling Curie-Weiss law. Curie-Weiss law. Okay, up to this transition temperature, it behaves as a ferromagnetic material. Beyond this Curie transition temperature, this behaves as a paramagnetic material. So earlier also I have discussed this one. When you increase the temperature, when you heat, or if you take any material, magnetic material, if you heat this material, these materials, magnetic material, loses their properties, loses their nature. Here also if you see this one in this curve, we are increasing the temperature. That means what? We are heating the material. Okay, up to particular temperature, these magnetic properties are increasing. Beyond that particular temperature, the magnetic properties are decreasing. Okay, that is what paramagnetic material is. Okay, so that is what equal. And also permeability also positive value and large value for case of ferromagnetic material. Okay, susceptibility is much greater than 1, and also permeability also much greater than 1 for ferromagnetic material. Okay, and next one, this we have discussed, and the examples are, you can write these examples. Okay, here very important property, this ferromagnetic material shows the hysteresis behavior or some spontaneous magnetization in the absence of external magnetic field. Okay, what is that? What is that hysteresis curve? We will discuss this one. So hysteresis curve, you can draw the curve between, this is applied external magnetic field on x-axis. On the y-axis you can take magnetic field, this is induced. If you apply some external field, there is a induced magnetic field will be generated. Induced means generated, okay, generated magnetic field. Or you can write magnetization, or you can write magnetization, I for magnetization. Or you can write intensity of magnetization, intensity of magnetization. Suppose if you apply some external magnetic field, the material is getting some magnetic field, or some material is magnetizing. So if you apply some external field, material is magnetizing. So that means what? The material is acquiring some magnetic properties. Okay. If you apply some external magnetic field, what happens here? Initially, the intensity of magnetization increases. Okay. Increases and further increases. It is saturate. Okay. This is what you can write here: saturation magnetization. Saturation magnetization. Even if you further increase this external magnetic field, there is no use of this magnetization, because already it is magnetized. Or you can write is also, saturation of magnetization. Okay. After that, further we will reduce. What happened to see what happened, we are reducing the magnetic field. Okay. Once we decrease this magnetization is reducing, but it is not following the same path, it is following different path. Okay. It is not following same path, and it is following different path. And at this point here, see point, suppose here 0 1, here 2, and at point 2 the material is having some magnetization, material is having some magnetization. But here applied magnetic field is 0 at point 2. Okay, at point 2 H is 0, H is 0, but that is showing some magnetic field or magnetization. This magnetization we are what we are calling this residual or spontaneous magnetic field, or residual magnetic field we are calling retentivity. Retentivity means it is storing some magnetic field. There is a residual magnetic field in case of, in the absence of external magnetic field also. Okay, this is you can write retentivity or residual magnetic field. IR you can write, or BR you can write. Okay. To make this residual magnetic field 0, we are decreasing the external magnetic field, external magnetic field. Or you can say we are increasing the external magnetic field in negative direction. We are increasing along negative direction to make this residual magnetic field 0. Okay. If you increase this one, it is following this path, and here it is 0 at point 3. You can write at point 3 the magnetic field H is not 0. Here we are applied some magnetic field, but here B is 0. So this particular field what we are calling cohesive field, cohesive field, cohesive external field. Okay. So we are further we are reducing, we are increasing the negative direction. What happens this one? It will increase again. It is saturating this one. Okay, it is saturating this magnetic field is saturating. Okay. So after saturation, there is no use of increasing the magnetic field. Then we are reducing the magnetic field. Okay. So if you reduce this one, it is not following the same path. It is following different path. It is following different path. Again, at point 4, it is having some negative residual magnetic field. Okay, it is not coming to 0. The material is having some stored magnetic field, or spontaneous or residual magnetic field. To make this residual, this particular magnetic field we are calling retentivity or negative retentivity. You can say negative retentivity or negative residual magnetic field. To make this one 0, we are applying here positive magnetic field, positive external magnetic field. Then it is up to here at point 5 the magnetic field is 0, but electric, this external magnetic field is not 0. So this one we are calling cohesive positive cohesive magnetic field, positive cohesive magnetic field, and after that it is reaching saturation. After that it is reaching saturation magnetic field. This one we are calling hysteresis loop or hysteresis curve. Only ferromagnetic material shows this behavior. No para and no diamagnetic material will not show this hysteresis curve. Only ferromagnetic material will show hysteresis behavior. Okay. So this is the hysteresis curve, very important. Whenever they ask dia para ferro, dia you write points and para you write, and ferro also you write the points, but you have to draw this hysteresis loop. Okay, hysteresis loop you have to draw, otherwise you will not get full marks. Okay, this is very important. In this hysteresis loop we have studied BS, this is saturation magnetization, and VR residual magnetic field or retentivity of magnetic field. So when external magnetic field is zero, but the material is having some residual magnetic field. So this particular residual, this magnetic field we are calling retentivity or magnetic field. To make this residual magnetic field zero, we are applying some external negative field, that is we are calling cohesive field. Okay, this is cohesive magnetic field. These two definitions you can know from this hysteresis group. Okay, so this is the about ferromagnetic material. Okay, is this clear, this this hysteresis two guys? Do you understand this hysteresis loop? Any doubt here?
One second.
Sorry, is it clear or any doubt? Okay, same will be we are studied in dielectrics, that is PE loop, polarization versus electric field. There also same thing, that is in case of ferroelectric materials. Okay, so here further if you see, okay, in ferro material, again there is a two type of classifications are there: anti-ferromagnetic material and ferrimagnetic material. Okay, anti-ferro and ferrimagnetic material, that we will discuss now. Okay, please respond. It is clear ferromagnetic materials? Any doubt in that ferro? No doubt. Any doubt, please? Is it clear or doubt? Nothing. Are you are you listening or not listening? No, no, man. So okay, I cannot ask frequently, very frequently. You are not responding. I cannot say anything. So that is even 4 5 days is over, then it's completed. Then it's not a thing. So anti-ferro and ferromagnetic material. Okay, we will discuss this one. So anti-ferro means here, this is the main important diagram. This is here spins are anti-parallel. Okay, spins are main very important diagram. This one, spins are anti-parallel. Okay, without drawing this diagram, whatever you write, no use. Anti-parallel and equal magnitude. Okay, equal magnitude. So this is very important point. So spins are anti-parallel and equal, or you can write spins are equal magnitude and anti-parallel. Okay, this is very important. You have to draw. Suppose they ask anti-ferromagnetic material, you have to draw this one. Okay, so after this one, the susceptibility also here small and positive for this material. Okay, small value, but susceptibility is positive value, and this is small. Okay, small value, and same thing permeability also. Okay, so this is very important point. You draw this one and you write this line. Okay, spins are anti-parallel and equal magnitude or equal this okay, you can write that point. And after that, This antiferromagnetic material also behave this Curie-Weiss law. Okay, this susceptibility is C by T minus Tn. T minus Tn. This Tn is called Néel temperature. Okay, Néel's temperature. Okay. Néel temperature. If you plot this graph also, just like we have studied Curie-Weiss law for ferromagnetic material. Here we will see this one. The same thing. Here susceptibility versus temperature. Up to particular temperature, this behaves as a antiferro antiferro. After that, the magnetization will decrease, and beyond this particular temperature we are calling Néel temperature. Beyond this Néel temperature, behaves as a paramagnetic material. Paramagnetic material. Here also always T greater than Tn. T greater than Tn. Here also what we have discussed just before point, susceptibility is positive but small value. Positive but small value. So when it is possible, when it is positive, only T greater than Tn, then in that case only the susceptibility is positive. Okay, this is also very important law. So you draw this you draw this equation and draw the figure. Okay, draw the figure. Okay, so this is the up to when you plot susceptibility versus temperature, the ferro antiferromagnetism will increase or susceptibility increase. Susceptibility is increasing up to particular temperature. Beyond this particular temperature, the susceptibility is decreasing. This particular temperature we are calling Néel temperature, and beyond this Néel temperature, this antiferro becomes a paramagnetic material. Antiferro become paramagnetic material. Okay, this is antiferromagnetic materials, and this is ferrous oxide, magnetic oxide, chromium oxide. These are some examples. Okay, next one, ferrimagnetic material. Next one, ferrimagnetic material. Okay, is this clear? Antiferromagnetic materials. Huh? So here see, spins are equal and opposite, so net spin should be zero. Net spin should be zero. So how they are having magnetic field? How they are having magnetic field? Please answer this one. Okay, earlier we have studied if spin is anti-parallel, equal and opposite, the net spin is zero, right? Net spin is zero. But how this anti-ferromagnetic material having magnetic field? Please answer this one, anybody, if you understand the question. So, if you don't understand, we'll discuss domain theory. In this domain theory, it will be clear. So, in a ferromagnetic material, there is a domains. Domains. In this domains, spins are like this. One domain like this. One domain like this, and one domain, one is up, one is down, like that. So all domain spins are not same. Okay, because of this one, this material having net spin momentum or net dipole momentum. That's why only these are showing some magnetic behavior. Okay, you got it? When we discuss this is domain theory, very important theory. We will discuss these points. Okay, how these are having magnetic field, even the equal and opposite spins are there. Okay, so this is antiferro and ferrimagnetic material. Okay, here the main difference between ferro and antiferro. In ferro, spins are equal magnitude and anti-parallel or opposite. Okay, this is the case of, in case of what? In case of anti-ferro. Anti-ferro. But here spins are anti-parallel but not equal magnitude. Okay, spins are anti-parallel. You can write the comment here. Spins anti-parallel, anti-parallel, but not equal magnitude. Not equal magnitude. Okay, the magnitude is different. That's why they are having net dipole moment or net magnetic dipole moment. Okay, dipole moment. So these are not equal, right? If it is equal, net magnetic moment is zero, but this is not equal. Okay, the magnitude, first one is different magnitude, second one is different magnitude. So net spin is between these two spins is not zero. And if you take all throughout the atom also, if you take all spins, their net spin is not zero. That's why this material is having some magnetic movement, here also you can see this. If you draw the diagram, susceptibility versus temperature, but here small difference is there. See, by T plus or minus, here Tn, T plus or minus Tn, this material sometimes behaves like this. Okay, positive and sometimes a negative. Susceptibility sometimes positive and sometimes negative. Here also you can write this T much T is greater than Tn. This Tn is the Neal temperature. Okay, Neal temperature, you draw this diagram and up to particular temperature, this here you can draw like this also. Okay, susceptibility versus temperature. Up to particular temperature, the susceptibility and ferrimagnetism is increasing. Okay, after this particular temperature, this is decreasing. Or you can say up to particular temperature, the susceptibility is increasing. But after beyond this particular temperature, the ferrimagnetic material becoming as a paramagnetic material. This transition temperature we are calling Neal temperature. We are calling Neal temperature. Here you can write plus or minus and T greater than here some examples are ferrites. Okay, examples are ferrites. Okay, susceptibility also here large and positive value. Here susceptibility is large value and positive value. Okay, it's large and positive value. And here examples you can write. These are the magnetic zinc ferrite, copper ferrite. Okay, these are some ferrites are the examples. Okay, some ferrites behaves as a this one. These materials also show hysteresis behavior. If they ask, if depends on marks, you have to write. Suppose if they ask 14 marks, dia, para and ferro, anti-ferro, anti-ferro and ferri. Okay, anti-ferro and ferri. You write the differences, all differences, and you write long answer. Okay, depends on. But here ferro you have to write hysteresis curve. This is very important. In ferromagnetic material you have to write hysteresis curve. Okay, if they ask or if they don't ask also, you have to write this behavior or nature. Okay, these anti-ferromagnetic materials and ferromagnetic materials also show the hysteresis behavior. Okay, so